Welcome to Unit 2, Lesson 3, where we're going to learn about geometric sequences and series. So by the end of this lesson and the second part that goes with it, you should be able to recognize, write, and find nth terms and partial sums of geometric sequences and use those tools to model and solve real-life problems. So in the last lesson, you learned about arithmetic sequences where the consecutive terms had a common difference. So now in this lesson, you will learn about a type of sequence called a geometric sequence whose consecutive terms have a common ratio. So if I asked you about the nth term of the given sequence, hopefully you'll notice that in 3, 6, 12, and 24, we are multiplying the previous term by 2 to get to the next term. So unlike arithmetic sequences where you were adding a common difference to each number, here we're multiplying by a common ratio. So that is the definition of a geometric sequence. It's a sequence where if the ratios of the consecutive terms are the same, then there is a number r such that when you take the second term over the first term, the third term over the second term, the fourth term over the third term, and so on, you get r, which is a common ratio of the sequence. So on example 1, let's determine whether or not the sequence is geometric, and if it is, let's find the common ratio. So if I look at example A, where I have 1, -2, 4, and -8, I have to look and see if they have a common ratio. So if I take the second term over the first term, it's -2 over 1. If I take the third term over the second term, it's 4 over -2. And then if I go ahead and take the next term over the previous, -8 over 4, I notice that all of them reduce to -2. Therefore, this is a geometric sequence where the common ratio is -2. Now let's look at choice B. On B, I'm going to do the same thing. I have to look and see if the second term over the first term is a common ratio of the third term over the second, and so on. Well, when I take 2/7 over 1/5, I can evaluate that complex fraction by taking 2/7 times the reciprocal of 1/5, which is 5 over 1, and that yields 10/7. Next, I take the third term, 3/9, and I have to divide that by the second term of 2/7. By the same process, I would take 3/9 and I would multiply by reciprocal of 2/7. 3/9 reduces to 1/3. So I get 7/6, and 10/7 and 7/6 are not equal. Therefore, this is not a geometric sequence because they do not have a common ratio between the terms. For example 2, we're going to write the first 5 terms of the geometric sequence. So the first way I want to show you is just by using that common ratio to multiply. You basically just keep multiplying by -1/4 to generate all of the terms in the sequence. It's not difficult. So my first term is 6. I get the next term by taking 6, which is a sub 1 times -1/4. So in a way, I'm defining this recursively, which 6 over -1/4 reduces to -3/2. Okay, I take -3/2, I multiply that by -1/4, which yields a positive 3/8. I multiply positive 3/8 times 1/4, which yields a -3/32. And then finally, for my last term, I get -3/32 times -1/4 to yield 3/128. So those are the first 5 terms of this sequence: 6, -3/2, 3/8, -3/32, and 3/128. But now I want to show you how we can define a geometric sequence using a sub n. So why don't you think about these exact same answers, they don't change, in the following way. Okay, I still start off with my first term as 6 because that was given. I can think of the second term as taking 6 times -1/4 to the first power to get -3/2. Now, notice how I did it before recursively, that I could take -3/2 times another -1/4. But if I think of this in terms of the first term, we're taking 6 times -1/4 times -1/4 again, which is squared, which yields 3/8. Again, to find my fourth term, a way to think about it recursively is that I took the previous term of 3/8, I want to multiply it by -1/4, or you're taking 6 times -1/4 times -1/4 times -1/4, which is 6 times -1/4 to the third, and that yields my -3/32. And lastly, for my fifth term, again, you can think of it recursively as -3/32 times -1/4, or that was my first term of 6 times -1/4 times itself 4 times. So this leads into the nth term of a geometric sequence. The nth term of a geometric sequence has this form: a sub n is equal to the first term times the common ratio raised to the n minus 1. Why is it raised to the n minus 1? Well, let's just look at that pattern from our previous problem. In our previous problem, notice how on the second term, I was taking the ratio to the first power. In the third term, I was taking the ratio to the second power. In the fourth term, I was taking the ratio to the third power. So you're always multiplying the ratio by one less power than the term that you have because you started with the first term of 6. If we have to write the first 5 terms of the geometric sequence and find the common ratio and find the nth term of the sequence as a function of n, what I've done here is given you a recursive sequence similar to the last problem. If a sub 1 equals 5 and we want to find a sub k plus 1 equals negative 3 times a sub k, when I want to find the next term is a sub 2, so I take negative 3 times a sub 1, which is the previous term, and I get negative 3 times 5, which is negative 15. To continue the pattern, I just keep multiplying the previous terms by negative 3. So I end up with 5, negative 15, 45, negative 135, and 405 as the first 5 terms of the sequence. So the directions also asked me to do the common ratio. So my common ratio is negative 3. And if we want to write a formula in terms of n, I need the first term and the ratio. So my first term is 5. My common ratio is negative 3. And when I put that into the formula, an nth term of the sequence as a function of n is a sub n equals 5 times the common ratio of negative 3 raised to the n minus 1. On example 4, you're being asked to find the nth term of the geometric sequence and to use a table feature of a graphing calculator to verify your answer numerically. So in this problem, you're given the first term is 8, that the common ratio is negative 3/4, and they want you to find the ninth term of the sequence. So in order to do this, we have to make a general formula first. So if we know that we're going to use the formula a sub n equals the first term times the common ratio raised to the n minus 1 formula, I know that my first term is 8. I'm given that my common ratio is negative 3/4. So when I put that together into a formula, I get a sub n is equal to 8 times negative 3/4 raised to the n minus 1. The problem wanted me to find the ninth term. So when I find the ninth term, I substitute in 9 for n. So the 9 minus 1 power becomes 8. Negative 3/4 to the 8 power is 6,561 over 65,536. And yes, I did use a calculator to multiply by 8 and reduce to yield my final answer of 6,561 over 8,192. All right, now let's check our answers using the table feature on our graphing calculator. So on my graphing calculator, I've already pulled up a graphs page. We need to change the graph entry edit to sequence mode. And our formula was 8 times the negative 3/4, all raised to the n minus 1 power. And let's graph that. And that's kind of interesting how those points are looking. So I'm going to hit my Control T, get my table of values, and if I scroll down to where my n is 9, I get the decimal point 800903. And what I did on the scratch pad previously was looked at our answer of 6561 over 8192, and notice when I get that decimal approximation, I get 0.800903. And this is the last example in this video, problem number 5, where we're going to find the indicated nth term of the geometric sequence. In other words, the directions are asking you to find a formula that you could find any term of the sequence. We want to find specifically the 22nd term of 4, 8, and 6. Since we were told this is a geometric sequence, we need to find the common ratio. So when I find the common ratio and I take 8 over 4, that's equivalent to 16 over 8, so my common ratio is 2. The first term is 4, and when I put it into the formula a sub n equals the first term times the common ratio to the n minus 1 power, then it yields 4 times 2 to the n minus 1. That's my general formula for this sequence. If I want to find the 22nd term, I simply substitute in 22, which is 4 times 2 to the 21st power. And yes, with my calculator, 2 to the 21st power is 2097152. And when I multiply that by 4, I get 8,388,608. So at this time, you are ready to work on the learning opportunity number 1, which is on page 582, 1 to 35 odd. Good luck.